the dimension reduction is a very big field within the machine learning. And there are many approaches have been proposed for dimension reduction. PCA is only one of these type of methodology, probably is one of the simplest method in the field of the dimension reduction. So we're going to talk about that. And if I have time, we can describe some of the applications that how this type of dimension reduction might be useful in practice. So what is the motivation here? So in general, the motivation for dimension reduction is this, right? Usually in real application, you are presented with very high dimensional data. And those high dimensional, come up with many different ways, right? For instance, you might be presented with images of different objects. So each image is a matrix. And if you flat them into a vector, that's very high dimensional. And you might deal with textual data sets, right? And for instance, you are dealing with the articles, different articles. You want to make a classification and of these articles, and you want to compare a different article to see which one is related to what. So in that case, your articles is just described by textual information. And the question is, how do you characterize the articles? If you use text, that's truly very high dimensional space. And another example would be in the financial market here. Suppose, and you look at the S&P 500 stocks. So that would be 500 equity stocks, right, associated with different companies. And however, those different stocks are related to each other. You might be able to kind of describe the overall movement in the stock market using only a few features, few things to describe, instead of describe an entire set of 500 stocks. So it might be possible to do that. So essentially describing a much simpler language instead of say, today this all 500 stocks, each one of them, this is the movement in this way. So that would be, you need a long list of 500 vectors to describe that. So, but however, you might be say, well, maybe the overall market is going upwards, maybe, and then there's differentiation between different sectors. Maybe you have technology, maybe you have energy and finance. So that you describe this way, you can provide much simpler pictures of that. So the question is, how do we, and in this case here, the question is, how do we identify underlying structure of that? So that would be related to the ideas of the dimension reduction. So I show one example here. Suppose you look at this data set here in a two-dimensional space. You have x1 and x2 here. And now suppose say, well, I might want to kind of reduce the dimension data from 2 to 1 dimension. What should I do? Well, the idea is there any way possibly you can describe your data x1, x2 using 1 variables instead of 2 variables? If you are able to do that, you are able to kind of compress your 2-dimensional data into 1-dimensional data. So how do we do this? Well, so in this example here, let's assume I have data x1, x2 here. Let's assume here x1, x2 can be modeled by one variable called z here. Is related to z times a vector plus another vectors here. And the question is, what is the z vector you should do? And then you have a single scalar move around that z vector, v vector, sorry, one single scalar z move around the v vector will provide you a good description of the data sets here. And so that's the idea. Well, you might want to think about it this way. And I suppose I come up with this directions here. I call this direction is my v vectors here. And now I'm going to describe each one of the blue dots here using a single scalar here. And with z here goes from 0, 1, 2, 3, and so on to describe this data sets here. And if you are able to do that, what this means, you map your kind of 2-dimensional data into what happens, only as one scalar that is associated with these directions of the v here. And more in this picture representation, what this means is, right? If I model everything along this z here, on this v here, the only thing you can model is this data will be straight along these lines of that. So this data, of course, will be different from the original data set here. However, it provides a good approximation to the original data sets here. And that's the idea of the dimension reduction. So you map to a kind of lower dimensional space, capture somewhat majority of the information on the original data sets here, and then make your visualization, make your data much easier to visualize, to analyze. And of course, you will lose information this way. So that is expected. So why the dimension reduction is useful? So there are multiple purposes for people using dimension reduction. So one very simple purpose is for data compression. And if you have high dimensional data, it somewhat makes sense to compress data in a low dimensional space such that you can only have a smaller storage to keep those type of data sets here. So that's one thing for data compression. So another thing here is this for noise removal. So that's actually very, in many cases, very useful. So idea is this, if you look at this two-dimensional data sets here, you can see they're spread here. It might be possible that the spread along the other directions here might be just caused by noise instead of real signal associated with the data sets here. It might be possible that because of the measurement noise, you will see kind of, your real model is along this direction, three directions here, but because of the measurement noise, you have data sets fluctuate around that. So by doing this type of dimension reduction, you map data sets along the Z directions here, and you maybe just happen to reduce noise, remove noise associated with the data sets here. So that's be a good kind of motivation for doing dimension reduction as well. So by removing the noise, and you try to extract the true signals from the underlying data sets there. That's one thing. And also third motivation in that. So in many cases here, when people are doing dimension reduction, it might be a kind of a data pre-processing step of later on supervised learning. So you might be say, I have a supervised learning problem here, but my input data set here is very high dimensional. It might be contains noise. And then what people say, let's do a dimension reduction first. And by removing noise, by maybe remove some other unrelated features from the data sets. So for instance, it's very well known that, so in many of the high dimensional data sets here, those variables in many cases are linearly correlated with each other. So when they are linearly correlated, which means even though you have two features here, x sub 1, x sub 2, because they are, maybe x sub 2 is simply 2 times x sub 1. So they are highly related to each other. So for that purpose, it might be good to remove one of them, and because it's redundant. If you introduce both of them here, and maybe during the process, you can overfit your models. So if you do a dimension reduction, it gives you an opportunity to remove those kind of collinear features of that. And in general, when you do reduce the feature dimensions here, the number of input is smaller, so you will have less possibility of overfitting your models. So that's another kind of motivation for performing this type of dimension reduction even before the supervised learning problem. All right, so I'm going to talk about one particular dimension reduction method here called principal component analysis. So it's a very straightforward methodology. I believe many of you already probably heard or touched these type of ideas before, so I'll go that relatively quickly. But if you have questions, feel free to stop me as well. So what is principal component analysis? Well, principal component analysis is this. Let me first talk about the procedural way. How do we do this? So to do principal component analysis, the first thing to do is to center your data. So center your data. So what I mean center your data sets here. For instance, you might have data sets here look something like this, but the data here, that if you look at the mean and of each x1, x2 here, they'll be centered around here. So to perform the principal component analysis here, you will need to subtract the mean along x1 axis and also means along the x2 axis from the data sets here. And another way you can think about it, you're going to shift the coordinate from the origin might be right now here, so that coordinate will be now centered. The origin will be at the center of the cloud of the data sets here. So this is a procedure called a mean centering. And that can be easily done. And how to do this? Well, you just calculate empirical mean of your data sets, and then you subtract the mean from each one of the samples. So by doing that, afterwards, your data, your transformed data sets here, x hat here, will have a zero mean. So that's called a mean centering, kind of pre-processing step. So that step, by the way, is used in many, many different places here. And I kind of mentioned that previously, even in the case of supervised learning, it's always good, sometimes good to do mean centering, to shift data sets and have mean zero in that. So that, but however, this is actually required for the principal component analysis. The reason I will mention that shortly, okay? So you do a mean centering here, and then next what I do here. So you have lots of data sets here, you look at this side here, and which direction you should map this data to, right? So which direction you should map this data here. And clearly from this one here, you can see I can choose direction V this way. I can choose direction V along the other direction with that. But if I project along the other direction, what you can see this, if I project direction along these directions, you will see all the data sets here after projection would be kind of a clustered and lumped together. So when you cluster together, you cannot differentiate the data sets here. And however, this V direction is good because if you along this direction, what do you see this? Original data set that is spread out is still spread out along the, even after the projections here. So the question is, how do you measure the spread out of the data sets after projection? Well, one way of doing this is to measure the variance of the data after projection. So that will be variance after along the Z direction. If you project data sets here, and what is the variance of this variable Z here? And that is the basic idea underlying principal component analysis. Essentially, and how do I find the direction here? I'm going to find the direction such that the data project to this direction have the largest variance. And if I have this motivation, and then I will have developed methodology to discover these directions back. So that showed up in this case here, right? Suppose now, suppose I'm going to choose a vector, a direction V. I'm going to project my data onto this V directions of that. And then the projected coefficient will be called Z variables here. That will be projected coordinate of each one of the data samples of that. So right now you can think about this X is a data matrix. The zero is the mean center of the data matrix here. So this would be each row represent one sample, and then each column represent different features of that. So if we use the N to represent the dimensions of the feature space, M represent the number of samples. So the X here will be an M by N matrix. So that is the data matrix we discussed previously. When you do X times V here, and that will be project each one of the rows, that will be each data along the V directions of that. So that would be, you can think about this would be coordinate of this data sample along this V directions of that. That's Z here. So Z will be a vector here, right? So now what I'm going to do here, I'm going to measure the variance of the projected points. And how to measure variance? Well, because in this case here, because your data is zero, have a zero mean here, as a result, this Z data here, projected points will also have zero mean. And just, because these guys have zero mean, if you calculate the mean of Z here, they will also have zero mean. So, and then the variance was simply the squares, summation of squares of each individual data point. So that's represented with ZI squares of that, and sum of them. And if I divide by M here, so that would be the variance of the projected points. So another way you can write down them is will be Z transpose Z here. So that would be the normal square normals of vectors of that. Or if you want to write down this explicitly in terms of matrix representation, so that would be becomes V transpose X transpose X times V here. And that is the variance of the projected points here. So now let's look at it here, right? So let's view this X transpose X here as something together. That would be just a matrix here. Let's view this as a matrix. This matrix here is going to be N by N matrix. N is the dimensions of your input data, original input. And the V now is the direction that I want to discover. And this direction I'm projecting my data points onto. So this is a V direction. And then V transpose times this matrix times V. Now this is a scalar, and that's representing the variance of the projected points here. And I mentioned that the principal component analysis is try to identify this direction such that this projected points have largest variance. So that's the main goal of the principal component analysis. Well, and how do I discover the V here, and I can formulate it as an optimization problem. And then optimization is formulated this way. So I'm going to maximize in these variance of the projected points here, and we calculated previously here, and with respect to different directions. So now in this case here, I need to kind of properly normalize the V, because if I maximize these guys here without proper normalization, then V can be chosen extremely large here, right? So you can choose V to be a extremely large vector, so you can maximize. So for that purpose here, we're going to normalize and make to ensure that to constrain that each one of the vector here is a unit vector, which means the norm is 1. The reason is that because I only care about direction here. I do not actually care about the magnitude of this V vector here. Because once I have direction, and then I can project my data points. I do not need to know the magnitude of that. So that's the reason I constrain V to be a unit vector, which means the length is exactly 1 here. So now I can convert the problem of identify the directions here to be simply this maximization of the projected variance, and subject to the constraint that this is a unit vector. And the question, I just need to solve this problem. Okay. And then if you remember from your linear algebra class, what do you notice that the solution of this problem here now is becomes simply V here to be the largest eigenvectors of this matrix here. And that you can demonstrate from your linear algebra. So how do you do that? Well, if you look at the X transpose X here, what are these guys here? Well, this guys here is simply the covariance matrix of your data sets here. Well, up to a scale here. And you have to do X transpose X divided by M, and that's the covariance matrix. But right now, I didn't divide it by M here, but loosely speaking, it's a covariance matrix here. So covariance matrix is a symmetric matrix, and also in addition is a positive semi-definite matrix, which means that that matrix has always have non-negative eigenvalues. So and you can do eigenvalue decompositions of this covariance matrix. And if you do that and then say, once I do eigenvalue decomposition, I want to identify directions of that. Which direction you do? Well, it'll be corresponding to the largest eigenvectors of this covariance matrix. And what would be the values of that? Well, that value would be simply corresponding to the largest eigenvalues of this matrix. So that would be the optimal values. And that's something you can show from the eigenvalue decompositions. All right. So this shows one kind of an illustration of that. So you have a previous data set I showed previous here. You center them. You can see now this is 0, had origins here. Now I'm going to identify this direction here. So by the way, this is a projection, showing you a projection along different directions of that. And now what we're trying to do is try to maximize the variance spread out of the data sets here after projection. You can certainly see that along this direction has the largest spread out, largest variance of projected points. And calculate that, and it turns out to be simply the largest eigenvectors of this covariance matrix of the data sets here. So this is a so-called principal component analysis. And then the question, right now, I identified the largest directions here. And however, you say, well, suppose I want to identify project data in a 2-dimensional space. Instead of 1 dimension here, I want to project it onto a 2-dimensional. How do I do that? Well, in the principal component analysis, what you do here is this. After you do this in a stepwise fashion, after you identify the largest direction, and then you identify the next direction, but you constrain that next direction has to be orthogonal to the previous direction you already discovered. If you do that, and then you can see that in this data set here, the largest direction now ought to be along this direction. That will be orthogonal to this first principal components. So, so this is not so useful in 2-dimensional space, but in a 3-dimensional space, that becomes more clear. Suppose this is the clouds of the data sets here in a 3-dimensional data points here, x1, x2, x3, x, y, z here. And this is the first principal direction. And that will be the first eigenvector of this covariance matrix. Okay. And then, however, if I want to project them in a one line, that would be the project data points here. So that's okay. But suppose I want to do better. Say, well, I want to project in a two-dimensional space to a plane instead of a line. How do I do that? Well, and I need to identify the second direction. So the second direction will be the direction that is orthogonal to this one here. And that will be, now you can think about this, there's a plane here that is orthogonal to this direction. And then within that plane, you want to identify that direction that maximize the variance of that. And if you do that, you will identify the second principal component. So that will be this side here. That will be two-dimensional projection. All right, so more specifically, so this is the kind of algebraic way of discovering the principal components. And you can also visualize this. And what does it mean about this kind of principal component analysis? Well, so essentially you can think about this. Suppose I model my data sets with using a normal distribution. Okay, suppose I want to make that assumption. I'm going to model that with single normal distribution. And then the normal distribution, what I need to specify is this covariance matrix. Okay, so I suppose I have that covariance matrix here. Now, once you have the covariance matrix you have, so this shows you something called and if you look at covariance, so along this ellipsoid here, and that gives you the equal density, equal probability density of that. And that's but in general, they'll show up as an ellipsoid here. So now, essentially, the ellipsoid here captures the overall distribution of the data sets here. And then the question, if I want to do principal component analysis, what I'm going to do here is it would be equivalent to say, I need to identify the major principal semi-axis of this ellipsoid here. So that will be along this direction. And then next will be the minor semi-axis that will be along the direction that is orthogonal to that. And that is the main idea behind this kind of in a geometric way, how do you view this principal component analysis? Instead of in the original x1, x2, so now I'm going to map them into this directions here, along this major axis here, and then will be the minor axis of that. And by doing that, those two directions are orthogonal to each other. So that would be, you can think about it in terms of geometric interpretations of the data sets. Yeah. Well, so more specifically, you can carry out this ones here by just carry out this so-called eigenvalue decompositions of these covariance matrix. So let's kind of summarize again what we talked about so far in terms of how do we do this PCA analysis here. Start with the mean subtraction, right? Subtract mean. After that, your data set have exactly zero mean. The reason for doing that because once you subtract the mean here, your variance calculation become easy, right? And because otherwise, your variance here have to subtract mean from the z here, and then this will not become this formula anymore. So that's really it's important to subtract mean first. So and then once you subtract mean here, and then you calculate the covariance matrix of your data sets here. So now if your mean is already zero, and that would be simply xi transpose of that. So that's covariance matrix. And the next step you do, you carry out the eigenvalue decompositions of this covariance matrix. And you have this eigenvectors along the V in the V matrix here. The D is a diagonal matrix, contains the eigenvalues of these covariance matrix. And the V here, so typically you can sort these eigenvalues from the largest to the smallest along the diagonal entries of that. If you do that, and then the first eigenvectors of V, which means the first columns of V matrix here, will be the largest eigenvector. And the second columns of V will correspond to the second largest eigenvector, and so on. And then the lambda 1 here will be the largest eigenvalue, will be the first entry in this diagonal matrix D, and so on. And then the principal direction will be simply the columns vectors within the V matrix of that. So in the PCA, typically you will need to choose how many, or what is the dimension you want to reduce, how much dimension you want to reduce. Or another way of saying this, suppose your original data set is n-dimensional. What would be the low dimension space you want to project it onto? And very typically, you might want to choose to be a two-dimension. So in that case, you can visualize your data in a two-dimensional space. And you can also choose something smaller, let's say 10 dimension, right? And that will be smaller than your original n here, and maybe 1,000. So now you can project in lower dimensional space. But that's something you have to decide. What's the number of dimension that's determined by you here. But then once you determine that, and that will be related to simply choose the first k columns from this matrix V here, and that will be the directions of the space, subspace you want to project your data onto. So that's principal component analysis. Okay, so in this way here, this is the most very natural way of presenting those principal component analysis, and to try to identify those principal directions based on the eigenvectors of this matrix S. However, in this representation here, in many cases, what people want to do is this, not only I want to identify the direction I want to project onto, but also I want to identify the projected points onto that subspace. And then how do you do that? What you do it is this, you take out each one of the directions, and now you take the inner product, each one of the data X with that direction, in order to derive the projected point. You can doable. And however, it will require you to do this additional second step. So alternatively, you can do this in one step by using SVD analysis. So that's also very common in carrying out this principal component analysis. Instead of calculating the covariance matrix, I can directly try to derive SVD representations of my original matrix, data matrix X. So let's see why this is possible. Well, suppose my original data matrix X here can be decomposed through this three matrix here, USV. So that is a singular value decomposition. So in this case here, it will mean that U is the orthogonal matrix, V is also orthogonal matrix, S is a diagonal matrix. And this is called SVD because U and V in general are different. So that's different from eigenvalue decomposition. In eigenvalue decomposition, U and V are inverse of each other. But in this case here, they are completely separate matrices. And then also X here is not a square matrix. So unlike in the principal component analysis, the covariance matrix is a square matrix, but X here is a rectangular matrix, is an n by n matrix. And however, you can see how this USV is related to the covariance matrix, because covariance matrix is simply X transpose X, if it is have a zero mean, right? And then in that case, you can see that the covariance matrix here is simply can be decomposed with VDV transpose here, which means VDV transpose is an eigenvalue decomposition of the covariance matrix. So put another way of saying this, once you are able to derive SVD representations of your original data sets here, and then this is V matrix here, it turns out to be the eigenvector matrix of the covariance matrix. So you can see there is a relationship between them. So which means if I am able to do SVD of the data matrix directly, and then this V matrix contains the principal components, principal directions of my PCA analysis, the direction I want to project onto. So in addition, so this U matrix here actually contains the coordinates of projections of data onto the lower dimensional space. And so by doing that, you do not need to kind of take an inner product between the directions of V and your data anymore. So you can directly take that from the U matrix. So this is SVD. So put it more specifically, and then you can represent them in this form here. So X here is an n by n matrix. U here now is also a rectangular matrix. If I'm determined, say, I'm going to project my data from n-dimensional space to a k-dimensional space, right? K could be 2, 3, to a lower dimensional space. And that will be U matrix here becomes a rectangular matrix. And that will be S here, this will be V here. So in general, the right-hand side will be not exactly the same as the left side here, because you are doing dimension reduction, you lose information. So that's reason this side here can only say it's approximations of the X here. They're not exactly equal. However, if you choose K to be exactly equal to N, they're becoming exactly equal. And however, if I use K less than N in general, is approximation to the original matrix. So that's a U matrix here. And U essentially contains coordinates of projections of X onto this direction V. But by doing this SVD, we were able to derive both principal direction and the projected coordinate at once. So that's the convenience of that. And also, you do not need to calculate the covariance matrix if you're able to do that. So that's kind of another way of deriving the principal component analysis is through this SVD analysis. So that's kind of probably you have not heard this before. You more likely heard this using this covariance matrix to derive principal component. I just want to say that if you're not comfortable with this, that's okay. And then it's okay if you're stick with this version. So they are equivalent. So, then, so if you're familiar with the derivation based on the covariance matrix, that's okay too. All right. So that's the the principal component analysis here. Let's see some applications here. Let me show you one application. I want to highlight that. So one application is this, and it is for analyze the data mining of the textual or documents. So nowadays suppose you have a yellow page on the Yelp. You have a lot of reviews, right? And on particular restaurant or something else, you have different reviews came from different customers. And so now you have lots of documents. Suppose I want to know, what are the, what's the similarity between different documents? And how do you quantify it? First of all, is there a way to quickly visualize the different documents, right? So I have many different reviews. Is there any way I can lay out those reviews in a lower dimensional space? I can see how the reviews are related to each other. So that would be kind of one way. One way of doing this is doing the dimension reduction, right? Lay down those reviews on a two-dimensional space. You can visualize them, and now you can browse them. So that's one thing you can think about. Another thing you can talk about this, right? Suppose I want to pick up a review that is similar to another review, and the question, how do you do this, right? So that is related to so-called text analysis in the field of data mining. It's very commonly used in different fields. But let's think about this type of application, and the question, how do we do this? Well, so first of all, you need to think about how do you represent those represent text and documents. And suppose now I have different paragraphs of the text here. How do you represent each individual paragraph there? So this in general is a very hard question because you can represent them. They are based on natural languages, and then you have to understand the meanings of the sentence in order to properly represent those sentences. However, to extract semantic meanings of the sentence here in general is not easy, right? You have to understand what the composition of the language, and from there understand the meanings encoded by the sentence. And so that's challenging. So in the data mining community, people have a very much simpler methodology to kind of represent text here using the idea of something called a bag of words. So the idea is I'm going to represent the text here instead of represent those in terms of the sentence here, but instead represent them as a collection of words. So essentially say, the only thing I'm going to care about are the words here, but the orders between words and does not matter. So in the representation backwards, essentially, in my representation, I mix them together and put them into a bag here and destroy all the order information, and then I use the words, a collection word, as a representations of each individual tag. So that would be a relatively simple methodology, but it turned out to be very useful. So in many cases, and it can do very well in many actual analysis of that. All right, suppose we stick with this representation here, and now think about how to represent each document. Well, so first of all, what I can represent is this, right? So I can generate a list of words, vocabularies appeared within a set of a document, a corpus of that. So usually that will be a long list of words. And then I have this long list of words. I can treat each word as a feature, right? As a feature here. And now with each one of the document here, and what I can do is this, well, I can check whether that word appeared within that document or not. And I can count them, how many times this word ability occurred within that particular document. So by doing that, I can now kind of characterize each document using a long vector, feature vector. So that feature vector essentially represents whether that particular word appeared within that document or not, or how many times this word appeared within that document. So that is kind of a bag of word representations of the document here. So for instance, let's take this list of documents as examples here. I have 5 documents in one set of documents, and then another set of documents here. Overall, I have 9 documents here. So in general, when I say speak document, it's not really a document here. Essentially, right now, it's a paragraph here, a sentence here. But you can think about that this way. You can extend that, have multiple sentences, multiple paragraphs. So I have 9 samples. 9 samples here. I'm going to represent each data sample with a bag of words representation. So by doing that, I'm going to create this giant data matrix. So my data matrix here, each row represents 1 data sample. So that will be 1 document. And then each column will represent 1 feature. And right now, because I use bag of words representation, that word is simply, 1 feature is simply say, how many times this word appeared within that particular document. So you have the matrix of that. And that's is a very popular way to represent a document using this type of bag of words representation. And of course, you can see this matrix here is extremely large matrix. And because in general, the number of words, possible words are very large. Depends on the vocabulary of a particular language. For English, the vocabulary will be, maybe within one particular card, you can throw away some of the non-informative words and keep only informative ones. But still, the vocabulary, the space of vocabulary is very large, 100,000, 50,000, something like that, right? So that would be very large matrix. And also, this matrix in general is a very sparse matrix, because for each document here, only a subset of words appear within that document, and the rest of them all have 0 entries. So as a result, this is very large matrix and also very sparse matrix. And so the idea is, can we project this document from this very large dimension of words representation into a lower dimensional representation? And so one way of doing this maybe is using a principal component analysis to project them in a lower dimensional space. So once you do this, and then you can carry out a lot of other analysis here. What you might be able, once you project in lower dimensional analysis here, you can carry out some supervised learning problem to document classification, or you can kind of in clustering documents, visualize them. You can also draw similarity between documents, right? So you say which one is similar to which another document based on this lower dimensional representation. And so you can see a lot of application in that field. Well, so let's think about this. Well, so this is somewhat kind of one example to illustrate that data matrix. So in this case here, in fact, one document is represented by columns here, but you can think about it in vertical way. So if you transpose this, that will be close to the data matrix we talked about. So these are the words here. This is how many times these words appear in each one of the documents. So that will be a data matrix representations of this list of the documents. So one way we can do this, one thing you can do, you can take out the principal component analysis of this matrix here, and by calculating the covariance matrix of the different words here, and by doing that, and then carry out the principal component reduction, or you simply do SVD of this matrix and then simplify that. So you can think by doing that, you might be able to derive so-called principal vectors. This will be the eigenvectors of the covariance matrix. So that is 2 examples of the principal components of that. So that will be the first principal component. This is the second principal components. So those are principal components here. That will be the direction. Essentially, these are direction psi. For this principal direction here, what are the how the words, what are the way of each word social with this principal directions of that? And the question, how to interpret this? I'm going to talk about it shortly. But this is one direction, this is another direction. So once you have these 2 directions so now you can represent each one of the document here with 2 numbers. And one will be the coordinate associated with coefficient associated with the first principal direction. That will be coordinate associated with the second direction. And now you can kind of lay out this entire document in a 2-dimensional space. And that will be something like this one here. So after you have this type of layout, you can see the relationship between different documents. So you might immediately say, well, these two documents are very similar, and this document is very far away, and so on. So make this type of statement. And after doing that, you can draw similarity between different documents, because now it's much easier to calculate, right? So previously, it's not so easy to calculate similarity between two documents, because if you're based on backward words, and many of them are not overlapping with each other, and so essentially it's impossible to calculate distance between them. Once you represent those entire data set, map them in a two-dimensional space, now you can easily measure the distance between them here. So that can somewhat show up in this side here. So let's look at what the principal components look like for this type of analysis. It's also called latent semantic analysis. So this is a representation of the first principal component on that data set. This represents the second component of that. And as you can see, so each one of the components contains a set of real numbers, continual numbers. Some of them are positive, some of them negative. The reason some of them are negative is this, because the vectors here has to sum to 1, and also this direction here is going to be orthogonal to the second direction. So that be kind of perpendicular to each other. So as a result, you cannot all have positive numbers. So it's just impossible. You have something, you need to have something negative numbers here to make sure that the inner product between these two are 0. So that is the show up is a extract the principal component on that data set that I showed you previously. You can see now it somewhat makes sense here, because the first principal component here talks about, the key words associated with these guys here. This is kind of, this is the weight of the words associated with this first principal component. So that would be, in general, a list of all words here. And right now, only listed those words with relatively large weights, and the rest of them have relatively 0 weights, which means not so important to associate with this particular PC components here. And you can somewhat get sense of what the principle look like. Essentially, we'll more or less talk about genetics, genes, SNP disease, and so on. So more talk about those kind of genetics of disease in this direction to that. So you can think about a lot of document in that corpus, in the analysis here, was done related to genetic disease, genetics of a lot of disease associated with that. That would be secondary directions of that. So that would be still be talks about the on the different types things here, and actually how to make sense of these guys here. Well, so in this case here, it does say a negative cell here, and these guys here have positive cell. So what does it mean here? Is that, so in this principal direction here, in the first principal direction, there's a lot of things talk about cells. In the second principal direction here, in those documents, in these directions here, actually there is a somewhat of deficiency of this word cell associated with the document. So that's where you have negative here, and so on. So in general, this type of thing will tells you, essentially what are the main topics associated with this corpus document you have here. And of course, this will be related to the data set that you are analyzing here. You can see this is very specific to the scientific document of maybe related to genetics of disease. So that's based on this type of document, we extract this type of principal component. And you can imagine that if you use other in a document, for instance, the Yelp reviews, and that principal component will be very different, but that will be based on that particular data set. All right, so this is called latent semantic analysis. You can see now, originally you have very long vectors here. It's very hard to analyze these long vectors based on simply backward words, but now you map them, much easier to do that. Well, I should mention that, and this type of analysis nowadays becomes very popular in many types of data mining and document analysis, text analysis of that. And in modern days, obviously, most of the analysis nowadays is based on this kind of deep neural nets based approach to that. But it somewhat is extensions of this idea I talk about here, but in a modern kind of approach to address this type of problem. And the problem, and things I talk about is more generically talk about something called a concept called embedding. Essentially, how do you represent a word or represent a sentence or represent a document using a vector, using a fixed set of vectors for that. And if you can represent them, well, that would be, you can do exactly the same thing I talked about. You can lay out in a lower dimensional space, you can do comparison, you can do lateral analysis. So these are embedding extremely important concept in the document analysis. So I talked about this latent analysis based on the principal SVD, principal component analysis. Obvious, this is a linear methodology because based on linear combinations of your input features, and you extend that into a nonlinear methodology using something called an autoencoder. So that becomes very popular topics nowadays. And essentially now you can think about a neural nets here. So this is the input of your X here, and then go through a hidden nodes here with a fewer nodes. And then later on, you try to produce something to be the same dimension as the input here. And then what you can do is say, I'm going to train this neural nets here to kind of reproduce itself. So which means the input is X here, the targeted output is also X. So by doing that, what's the purpose of that? By doing that, essentially, I try to find a representations of X through a lower dimensional number of nodes, lower dimensional here. And then later on, I can also reconstruct X in this way here. You have this encoding layers of a set of networks here to encode those input here using a lower dimensional features here. And then you decode them, try to reconstruct them. And then the way you can train them, say, I want to make sure the output here is the same as the input here. You can formulate a loss function this way, and then you can train model this way. The benefit of this type of models here is now you can construct those low dimensional features through nonlinear methodology. So PCA is fundamentally a linear method because each of the features here is linear combinations of your input dimensions of that. However, by using this neural nets, you can generalize that. And this type of framework is called autoencoder framework, and now becomes very popular approaches in the unsupervised learning, and people generalize them in various different directions. That you have a deterministic autoencoder, or you can have a probabilistic autoencoder. One of them is something called a variation autoencoder. It becomes very popular models in the field of the generative models. Nowadays, you can use this kind of variation autoencoder to synthesize images and looks very realistic. You cannot distinguish those so-called fake images from the real ones of that. So a lot of direction in that side of that. And there's a related concept, something called embedding. I just mentioned that. So particularly something called word to vector embedding. In that case, it will be not only embedding the sentences I talked about here, and you can find embeddings of the individual vocabulary, individual word. And there's a way for doing that. So by doing that, now you can have continuous representations over those discrete concepts like words, the sentences. And now you can somewhat take into consideration not only the bag of words, but now the relationship between words within a sentence of that. It's somewhat taking the semantic meanings of the sentence into account by using the modern idea of the embeddings. So I will not go into this, but a lot of progress has been made recently in this direction. So I find a few minutes, I want to talk about another application here that has been very successfully used using this kind of principal component analysis and also the ideas of the SVD analysis. This is a very big field in something called a collaborative filtering, and it's very useful behind it's a very fundamental element behind many kind of recommender systems. So in the industrial application, deep learning probably recommender system is probably one of the major, probably most widely used applications in deep learning because it was used in many commercial online website so that you can make recommendations. So most of the, nowadays, most of many e-commerce or many online platforms, so they get a lot of user data sets, and by doing that, they can make very smart recommendations of the product, services, and sell this product service to you, and so on. So a general problem in this guys here is this. So how do you make recommendations of product, services, and so on? So there are multiple ways for doing this. So in general, there are different approaches. One approach here is based on something called content-based approaches. So in the content-based approaches here, essentially, in your algorithm build a profile of your users based on the previous purchases. And if a user, let's say in the Amazon, you bought this n number of products before, and then we can build an algorithm talks about what are the somewhat preference of the user here, what type of product this user might be interested in, and once we know this preference, and then we can make a recommendation. So this type of recommendation is something called content-based. The reason it's called content-based is because my recommendation is based on this user's previous purchase and those product purchased before, and then I have a good understanding what type of product it is, a good characterizations of this product. And that's you know, because I know this product and you bought this before, so I have a good idea what type of future product you might be interested in as well. And then there's something called knowledge base here, because content base here is this, right? So you might be limited in number of products you bought before, right? However, I can kind of extrapolate other products you might be interested in. And how do I do that? Well, all the products are related to each other through some relationship. And in that case, what the algorithm typically do is build a knowledge graph first. So you have a knowledge graph in terms of and now it tells you relationship between different products. And now if you bought this product A before, and because based on the knowledge models, I know that B is closely related to A, and now I can recommend B to you. So that would be knowledge-based model. So there's another methodology here, something called collaborative filtering. In this case here, I do not utilize any product information or user information. I purely based on, you know, tells you users' preference based on what's are popular among the other users that are similar to this particular one, and based on the peers. And let me show you what I see here. Well, so let's look at this kind of a very famous so-called the Netflix movie recommendation example, and it'll be very well studied in the community here. So in this case here, essentially, you have this each movie here, show up each rows here. You have many movies, each movie in a row here, and each column represents one user. The number here represents the rankings of the user on that movies. So that's called a movie recommendation. So once the user watches the movie, they put a score here, the scoring to that. And now usually this type of matrix here is very sparse because each user most likely watch only a small number of movies, and one movie is only watched by a relatively small number of users, right? So that in general is a very sparse matrix. However, from a Netflix point of view, and it very much would like to know what are the preferences of each user here for all the movies it might have here, because even though for this, for instance, for the movie 5 here, it hasn't watched the movie 1 first. If I know the scores here, if I know that the user 5 will rank movie 1 very high, and then most likely I would like to recommend the movie to user 1 here. And if I know the scores here. However, because it doesn't have ranking, how do I identify the missing scores here? Well, so previously the content-based approach would be say something like this. I'm going to build a profile of these users based on the previous movies here. And for each one of the movies here, and I will pull out, say, what are the style, genre, and the movies, and then characterize the movie using a set of features. And then based on these features here, I have a rough idea in terms of what this user might like, what type of movies. And for the first movie, I also have a good characterization of these guys here in terms of these features. And then I'm going to learn this movie based on this feature representation. This is a content-based approach. So in this alternative approach is something called a collaborative filtering. And then the idea is, and suppose you have no idea what are the movies are, and they're just numbers here, and you do not know what are the contents of the movie. You don't know the title of the movie, you don't have anything. The only thing you have is this ranking matrix here. You know that the movie 1 is ranked with this score by this number of users here, and this user ranking is here. And the only thing you have this matrix, and the ranking score, and that's it. You don't have anything else. So now the question is, how are you going to provide a score on this movie 1 for the user 5 here? Well, so in order to address this question here is this. So what this fundamental, what this algorithm we're trying to do here is this. Well, I don't know anything about this. However, what I noticed is this, based on the previous history, I know that this movie 1 typically is very highly related to movie 6 here. Okay, based on the user's previous ranking, you realize that. And if movie 1 is ranked high, most likely movie 6 is also ranked high, based on this vector here, similarity between them. So now, based on this idea, I can extrapolate that because, you know, movie 6 is very similar to movie 1. So now, this user 5 ranked 3 on the movie 6, and most likely it might be ranked 3 on the movie 1 as well. So that's the idea. So it's kind of a so-called collaborative theory. So your ranking here is based on your peers' rankings, your other people's ranking here. Because you didn't rank this one here. However, I do have this movie here was not ranked by 5, but I do have other movies here ranked by this user here. So you can extrapolate that. And so more specifically, how do you carry out this, implement this kind of collaborative theory methodology? And one way of doing that is by doing this kind of the SVD analysis. So you can think about this. I have this data matrix here. And what I can do, I want to decompose this matrix into a kind of so-called another matrix here, a lower rank matrix here with only 3 columns. And then another matrix will be users here. You can think this is something like SVD analysis of this matrix here. This is your X matrix here. This is U, this is the V. So I can combine that diagonal matrix, merge it to one of them here. So now in the end, I have the U and V here. And you can think about this, you know, principal direction. This will be the, you know, coordinates of that. So there will be characterizations, the user's preference along this hidden latent representations of the movie. So this is latent representation of the movies here. And now this each user, you have a latent representation. In terms of latent representation, what are the preference of this individual user? And then you take a product between these two. And now, so what, now the power of the problem now is this here, right? So suppose once I identify this U and V matrix, and then I can fill in all entries of this entire matrix here because I find approximation to that. So that's good. However, many of you now quickly realize I cannot carry out the SVD matrix of this matrix here because there's missing values. There's missing values. How do I do SVD analysis? So you cannot do it, right? You know, so another way, what we can do is this, instead of directly perform SVD analysis, but instead you say I'm gonna approximate this matrix here with these 2 matrices here. This is called 2 latent space representation of that, and then I can optimize those parameters within this matrix here. So in the end, I need to identify the entries, this item matrix and the user matrix. And how do I do that? I try to minimize the difference between this matrix and these guys here based on the known content here. And by doing that, you can solve somewhat a least square problem. But in this case here, your least square contains 2 sets of parameters. And however, there are optimization algorithms to solve this problem here. But then in the end, it looks like SVD, but in more generic form because you have missing data there. So by doing that, now you were able to kind of, first of all, fill in the missing values, but also you can lay out all the movies, let's say in a 2-dimensional space. You might have one latent representation in this direction, another latent representation, another direction there. And indeed, people discover that you might have, you know, one direction corresponding action movies and other types of movies, and then you lay out the entire representation of movies on those type of latent space representation. So that's very, very nice to visualize this type of data here. And so that's what I talk about in terms of optimization here. Essentially, you need to solve both U and V here, and then you can take the difference between them, and in the end to minimize them. And you can use gradient descent methodology to solve this problem here. All right, so that's what I want to say regarding this kind of a latent representation dimension reduction analysis here. And so that's pretty much summarized what I want to say regarding this unsupervised